Droid cam. Switch cameras. Switch back. There I am. Okay, great. So if you all can hear me, please put a 1, 2, 3 in the chat or in Discord, whatever works for you all. Just so I know that you all can hear me. Okay, there's a 1, 2, 3 from Tanuj. Good. So we have someone here who can at least hear me. So I'm gonna just say again in the Discord. This might echo, but I am now streaming on Twitch, so make sure you all join me there. Okay, cool. I'm gonna just type in chat. You all wanna join the meeting? This channel is for questions. Okay, just in case we have some late joiners. So, thank you all for joining me again. We have Tanuj, Shrethi, and Aiden in here. So last week we got to this point with the Pokeballs for the main gearbox plate. Today the goal is to get us to this point basically. I want to have all of the gearbox done by today. So we're going to make a second plate, we're going to insert a lot of components, and then we are going to go back in and fix a few things because there are some issues with this plate that we will learn about later. But in the meantime, we'll just go through. So at the end of last meeting, if you all remember, we made the plate and then I told you all to insert the bearing using MKCAD. I'm going to pull open you all's documents quickly just to make sure everyone is at that point. I believe Tanuj went ahead and added the motors. Okay, open Shrethi's document here. I see a bearing. Good. Here's Aiden. I see a bearing in there as well. Okay, cool. So let's just go ahead and go through and start adding more stuff to this assembly. So we're in drivetrain A gearbox. My voice just cracked there. I've been talking a lot today. I'm sorry. So now what we're going to do is we're going to go ahead and add in the sim motors, or the mini sim motors specifically. So again, we're going to go into MKCAD, and we're going to go to the MKCAD motors. Here it is, motors. You can add in their configurable motor. I'm just going to add in the straight mini sim motor. And I'm going to make sure I click that 3 times so I have 3 mini sims here. So now you can see I have these mini sims out. One of the cool things that MKCAD does is it gives you the mate connector. As you all can see, that mate connector kind of buried in there. That's the mate connector that you want to connect with the face of whatever you're working with. So I'm going to do some fastened mates. I don't know why my mouse keeps auto-zooming me out. I'm going to put my main mate connector over that mate connector in there. I'm basically going to select the middle of this face, and I'm going to go ahead and insert that down here. Now this is on the wrong side. I want it on the side the bearing is flanged out. So I'm going to put it on the right side. And I also want to make sure the holes, because mini sims have 2 holes, I want to make sure those holes align with the holes that we have in the gearbox plate. And I can see that they do align perfectly. So one thing I'm going to do is, I always suggest doing this, renaming your mates, because it's awful when you have like 20 or 30 mates and they're all just like fasten 1, fasten 2, fasten 3. I just name the mate after whatever we're mating. So here I'll name this mate Minisim. And then I'm going to go ahead and mate the other 2 parts. So I'll mate you with you. Make sure I flip you around. Make sure the holes are aligned. They are. So it seems like this one is having a little bit of an issue. Seems like I'm not perfectly aligned. That might be something I have to inspect later, because I'm getting a little bit of a tolerance variation there, but I'll inspect that later. Mini sim, that's going to be that mate. And then we're going to mate you. Grab you, I can actually just turn you around towards me. Mate you to you, just grab you from the back side. I need to rotate you once to make sure the holes align. And I'm going to name you Minisim. Great, I have 3 Minisims. if you ever have these weird mate connector icons stuck on your screen, you can press K on your keyboard and that will just get rid of them. You can also press K to bring them back, but I like getting rid of them. So I wonder why that is being an issue. Oh, I see it. I must have put these holes too high up. I'm gonna have to go in and fix that later. I'm not gonna worry about that right now. What I'm going to do is I'm going to actually leave a comment on this because that is best practices. Add comment. Need to lower middle mini sim mounting holes. They aren't line with center hole. Adding comments to Onshape documents is a very useful feature that we will be using, especially next season, just because it is helpful when you need to communicate from one person to the next. Now, I'm trying to see something. Let me check something. Okay, that's interesting. So, one helpful little trick. Wait, Tanuj says, wait, I don't have the issue with the sim hole lining up. This might have just been an issue on my end. So if you don't have that issue, that means you're a better CADer than I am. So I must have messed up something when I was building it. So one helpful trick that I use a lot whenever I'm building assembly, if you right click on your main assembly up here in the upper left and you hit check interferences, what it will do is it will check if there's two parts that do not go together. It's basically checking if there are two parts overlapping, and those appear in red. So as you see, I'm running an interference check, and what's actually happening is the mini sim that I've inserted here, the outside of the kind of like part that comes off the shaft, I don't know what you call that part of the mini sim, that's actually interfering with the gearbox plate. And so basically the hole in the center of the mini sim is too small. So I'm actually going to have to make that larger. I want you all to go into your assemblies and do an interference check like I am and see if you're getting these red marks. Because whenever you have red like this, that means it's bad and you need to fix it. So what I'm actually going to do here is I'm going to delete this center mini sim and I'm going to check some dimensions here. I'm going to grab the outside of you and you have a diameter of 0.075 or 0.75, so 3/4 of an inch. And the inner diameter of this hole is, I clear my mouse, 0.74. So that's a key difference here. There is a, this mounting hole, or this center hole, sorry, is a 100th of an inch smaller in its diameter, which means if I were to actually go out and manufacture this plate, it would not fit with these mini sim motors, and the mechanical assembly team would be very upset with the CAD team. How do you do that again? So up here, you're going to make sure you're in assembly. You're going to left click up here at the very top of your instances. So you're going to select everything basically. You're going to right click and hit check interference. So now you can see I'm interfering on the shaft just because I moved the motor out of the way. But basically anywhere you have red is going to be an interference. So I'm going to take this opportunity to do is go back into the drivetrain part studio and modify the main sketch in a few areas. So this sketch is very messy. It would be wise to actually go in and clean it up a bit, but that is something you could do later on. What I'm going to do is find anywhere that I have these center holes that are 0.74 inches, and I'm going to make them 0.7505. I'm just going to make them ever so slightly larger. Now, I'm doing 0.7505 for a very key reason. Whenever you manufacture something on a CNC router, there's always tolerances that you have to be wary of. So even though these mini sims have a this part of the mini-sim is 3/4 of an inch exactly. If you use your router and you cut out a 3/4 inch diameter hole and you try fitting this on to that plate you just machined, they're probably not going to fit together because your CNC has tolerances. It could be a little bit small, it could be a little bit large. So it's almost always required whenever you're seeing something to add in that tolerance. And typically I do about 5/1000ths of an inch worth of tolerance. It really depends on what you're doing. If you're like doing holes for mounting gears, which we will be doing here in a second, you might do 2 to 3 thousandths of an inch. But for this case, we could go a little bit larger. I'm going to do 5/1000ths of an inch just because this hole isn't as crucial. It's not really supporting any weight. So yeah, we are going to make sure those are all 0.7505. Sorry. Then I'm also going to try and figure out why these holes aren't aligned. Give me a second. If I do a little bit of investigation work here. So what? You and you are horizontal. I'm going to delete that horizontal mate and I could try something else. Sometimes this just takes a little bit of trial and error, and you'll have to give me a second here while I try and figure this out. Why does my on-shape keep zooming out automatically? So if I click on the center of this hole and I click on the center of this hole and I do a horizontal mate, there we go. That fixes that. And now these holes are perfectly horizontal to this center hole, but now these guys are giving me an issue. So now I need to try and figure out what mate is preventing this. So if I look at you, so that's a mirrored instance, that's a mirrored instance, that's a mirrored instance. So these are the originals. This side is perfect. This side is not. And because these left guys are mirrored, as you can see with these little icons, if you ever want to know what type of constraint a line or a circle has, if you just hover over it, a little icon will appear. And this little hourglass icon is a mirror icon. So that means when I mirrored these lines over here, they're not perfectly aligned. So that means this guy must not be horizontal with you. So now I need to figure out what's going on with this guy. Just give me a second here. Come on, why are you zooming out? This is the majority of what you do when you CAD. You troubleshoot why things aren't working as you expect them to. Should be normal. Tangent, tangent. Incident. I'm going to delete some of these mates and just try and see if I could get them to... Interesting. That doesn't solve my issue. You to you. Why am I having... Okay, if I drop a construction line between these two, you can actually see that the construction line is not flat. It doesn't even intersect with that. So if I actually make you and you incident, it's going to pop up a bunch of errors. And that actually helps me because it lets me see which constraints are causing conflictions. So maybe you are. Let me try deleting you. Ah, there we go. I found the constraint. That was the issue. Make you and you incident. Okay, there we go. Now, that should have fixed all of my issues. Let me remate this guy onto here. Rename you mini-sim. Okay, cool. Now my holes are perfectly aligned. So if you all change the size of those center holes from 0.74 to 0.7505 or anything larger, and you run an interference check, you will notice it will say no interferences. So hopefully you all are at this point where now you have no interferences with your sketches. And yeah, hopefully you all have the bearings and the 3 gearboxes. I just noticed Angini joined, and Angini, I noticed you made a document earlier today. I'm just going to pull yours up. So it seems that you have caught up to where everyone else is, which is impressive. So good work. Let me know if you have any questions about how everything is going. But it's looking like everyone has everything going well. Okay, cool. So let's get on with it. No more waiting for me. What is the next thing that we should add? So the next thing that we should probably add, let's do the motor pinions. So we're going to add in these tiny gears. So on the on 1678's robot, they use 11 tooth pinions. And now we're going to learn a little bit about gears. So we're going to go back into MKCAD. Oh, really cool feature I'm going to show you all right now. You all don't have access to this. You can request it on Chief Delphi if you want. But MKCAD recently added their own Onshape like app. And so now, because I'm part of the private beta testers, I have this nifty little icon over here to my left where now all of the MKCAD parts are right here. I no longer have to go into like the public documents or add in my own tags or whatever. So I have this nifty little thing. This will be available to all soon. You can also request access to the private beta on Chief Delphi. So just a little bit of flex, but you all should get this. Hopefully, if it'll go public here in the next few weeks. Basically, we want to go MKCAD. We want to go to gears. Gears, here we are. And we want to find the 11-tooth 20 DP steel sim pinion. This guy right here. Key thing. 11 teeth, 11T, 20 DP steel sim pinion. So all of those mean something very important. So we're going to add in 3 of those. Let me get a drink of water quickly. So there's a lot of important things to look at here. First of all, 11T means 11 tooth. We talked about that in previous weeks, that we are using 11 tooth for our driver gear. Now 20 DP. 20 DP is very important to know here. DP stands for diametrical pitch. And basically what that is it's a ratio to the number of teeth to the outer diameter of your gear. Actually, I believe it's the diameter between the base of your teeth and the top of the teeth. So basically, when something says it has 20 DP, that means that any 2 gears that are both 20 DP will mesh with each other. So if you had a 100 tooth 20 DP gear and a 10 tooth 20 DP gear, they will mesh together. Their teeth will fit together perfectly. This is in contrast to a lot of these gears on here are 32 DP. So if I pull up like a 32 DP 12 tooth pinion, and I pull that out right here, you can notice that here on the left I have the 32 tooth. Here on the right I have on the left I have the 32 DP, and on the right I have the 20 DP. These 2 gears will not mesh with each other. So you must make sure whenever you're building a gearbox, all of your gears have the same diametrical pitch. In FRC, we almost exclusively use 20 DP gears. You should never really use 32 DP gears. 32 DP gears are typically used in first tech challenge where you have lighter loads. But it's important to know that if you're ever making a CAD assembly and you accidentally pull a 32 DP gear, it's not going to work. And if you go on VexPro and you're buying gears, you might accidentally buy a 32 DP gear instead of a 20 DP gear. So always, always, always buy the 20 DP gears. On top of that, I'm going to just pull up the motors quickly. Not the motors, where are the gears? So we had 11 tooth 20 DP steel. You could buy either steel gears or aluminum gears. Personally, I'm in the boat of always, always, always buy steel gears because we saw what happened last year with Rosie and its gearboxes. Aluminum gears don't last as long as steel gears. They're a lot lighter, and so a lot of teams will say, use steel or sorry, use aluminum because you'll save a few pounds on your robot. I think that's not true because a full set of gearboxes with aluminum gears will weigh maybe half a pound less than of 2 gearboxes with steel gears. And a half a pound is not going to make a significant difference in FRC. If that is pushing you over the weight limit, you have other problems to deal with. So I'm personally always in the boat of always buy steel. And then sim pinion just means that this is a sim style, or this fits a sim style motor. So we have the 8mm keyed shaft that is common in sims. This is in contrast to these Falcon pinions. So Falcon pinions have a Falcon spline in them, and if I pull it out, that's a sim. That's the Falcon. So if you're running a Falcon 500, that's the shaft you have, versus if you're running a sim style. So that's all the explanation I'm going to do for that. Delete you. So hopefully you all have your 11 tooth 20 DP steel sim pinions. I'm not going to CAD in the keys to these motors because I'm not that petty of a CADer. I will not CAD in the keys, though I have done it before. We're just going to mount these straight onto here. So I'm going to fasten to the back face of the mini sim. That's what it's called. And then I'm going to offset it by about -1/4 of an inch in the Z axis. And that's just going to pull it kind of towards us. So I want to name this. I'm going to name this 11 tooth pinion, just because I like naming my mates. And then I'm going to mate the rest of these, flip you around, rotate you so the keys match up, just because it's going to annoy me otherwise. I'm going to do an offset of -0.25. Now, I'm actually going to change something. This shouldn't be a fasten mate because technically these gears spin, so these should actually be revolute mates. So I'm going to do a revolute mate, and I'm going to change that one we just made to a revolute mate. And that will, I'll show you a cool thing you do with that later. So I'm just going to do this last one. I'm going to turn you into a revolute mate, rename you to 11 tooth pinion, offset you by -0.25 inches. So now you all should have your gearboxes looking like this, and your theoretically these should spin. Oh, my plate's not fixed. I'm gonna fix the plate quickly. If you right click on your a part and you hit fix, that will just make it so it doesn't move, and that allows you to play with your parts. So Onshape isn't liking this right now for some reason. Oh, can you explain the keys? Keys, yes, I can gladly explain keys, Aiden. So I'm going to make this less transparent. So this is how motors in FRC typically work. What you have is you have a shaft, just a standard circular shaft that is almost a press fit, but then you have these slots in them, and these are called key slots. Basically, what you have in this key slot is you have a tiny long piece of aluminum. It looks like I might actually have an example here. If we go into public, I've inserted them before. Sim key. I'm pretty sure Rosie, or not Rosie, I'm pretty sure StealthBot has keys modeled in. Here we are, 2mm key. So I just searched this up on whatever the heck. There we go. I'm actually going to grab one of you as well to show you what these guys do. So these are keys. You all have probably seen them before, maybe didn't know what they are, but these go right in here. You don't have to model this. I'm just going to model it just to show you. So you insert the key into your sim shaft, and then you will put your pinion on top of that. And basically, that prevents the pinion from rotating like how I'm rotating it right now. It locks the rotation of the shaft and the rotation of the pinion together. And that's why these pinions have these little slots in them, so they can accept the key that is already on the shaft. You don't have to worry about this now, because if we look at a Falcon 500 motor, which are the motors we typically use, or probably will be using going forward, the Falcon 500s can actually come with a keyed shaft. Let's look at the long shaft. There it is. So the Falcon 500s do not have keys, they actually have splines, and so that allows the pinions to kind of fit on however. But like any other motor that we use, whether it's a sim, mini sim, a Neos have keys, all of those you'll have to worry about making sure you have your key in your CAD file, or in your final assembly. One other little thing that I want to show is the 8mm push-on retaining ring. So these you'll sometimes get in your baggie of stuff when you actually order your motors. And these are just little rings that get pressed onto the end of the shaft like so. And they will grab on. They're one-way rings. So when you push them onto your oh, sorry, I actually did this backwards. When you push them onto your shaft, they will not want to come back out the other direction. It's actually supposed to be like this. I can mate. Again, you do not have to model this right now. I don't even believe these are in MKCAD. Holy crap, why is my voice so dead right now? But basically, they go on like this, and they prevent the pinion from sliding off the shaft. Typically, the pinion is on there pretty tightly, so you won't have issues with this. But you might as well put them on. One of the other great things about the Falcon 500 is if I pull the Falcon 500 back up, motors, Falcon 500, look at the long shaft, insert you again. The Falcon 500 actually comes with a hole down the middle of it, and what you do is this hole is threaded to accept like I don't know if it's like a quarter 20 or a number 3. I don't know what type of bolt it accepts, but basically you put a bolt and a washer on the end of it, and that's how you retain anything on the shaft. Sim motors don't have that luxury, so you gotta use these rings. But again, I'm not gonna worry about that for right now. That is just a teaching thing, so I'm gonna delete both of those. Hopefully you all are still with me. This is how the CAD meetings are gonna be going, kind of for the remainder of the design of this robot. Just so you all know, I'm gonna be showing you how to design these things and just teaching you along the way all of these minor details that you just pick up over time, and that are hard to teach someone if you're just teaching robotics. But these minor details are important if you actually want to design your own robot from the ground up. So just know that all of these little things that I'm teaching you do come into play if you wanted to build your own robot from the ground up. Anyways, let's continue moving. Basically, the next thing I want to do is, now that we have the pinions on, I want to add on to this main gear. But before we add on the main gear, we actually need to add a hex shaft. The hex shaft will go through that bearing. So I'm going to go back to my document, and we are going to learn about shafts. So if we go into MKCAD, and you all will have to do this through your insert menu, and we go to shafts configurable. This is what we're going to use. So you might have to search this up in the public documents, just MKCAD shafts configurable. So this is going to give us a lot of options here. And we're going to kind of go through all of these so we can learn about shaft retention today. So the first thing I'm going to do is I'm going to set the shaft length, the effective length, to some high amount. Let's say 7 inches. I'm going to wait just a second so you all can actually get you this configuration menu. Man, I need like some throat lozenges or something, because my voice is kind of dying. Okay, where does the Loctite go on here? I will show you. Loctite goes on anywhere you have threads. So if you are threading on something, you put Loctite, just as a general rule of thumb. The flavor of Loctite depends. So hopefully you all are at this menu. I'm just going to show you one of these shafts, and then we'll go into more depth. But basically, I want you all to insert a 7-inch effective length. We're going to go with a 1/2-inch hex shaft, not thunder hex. And we're going to have both of the retentions be snap rings. And then we're going to have include and merge. And we're not going to click on the bearings. So 7-inch, 1/2-inch hex profile. We're going to hit inserts. It'll take a minute. But here we go. If I pull this out to the side, here's the shaft. So there are 2 key things I want to teach here first. Or there are a bunch of key things. I shouldn't say 2. First, I'm going to copy this shaft, and I'm going to change the configuration of 1 to thunder hex. And so first, we're going to learn about the difference between thunder hex and hex shaft. Can I repeat that? I don't know what I'm repeating, but I think you're talking about Loctite. What was I saying? Oh, Loctite. Loctite goes on anything that you have threads. So if you are threading something like a bolt onto a nut, or a bolt into a threaded insert, or something like that, you are going to need to use Loctite. Probably. So for some reason, that is giving me an error. I don't know why. I'm going to insert another shaft quickly.
Can you repeat the shaft configurations?
Yes, I can repeat the shaft configuration. Thank you for speaking up. So we are going to go into shafts configurable. We are going to do a 7-inch effective length. You're going to do a 1/2-inch hex, and then everything else will stay the same. You want to do snap ring for both, and include and merge everything for both. And we'll go through all the options here in a bit, or most of the options. We won't go through everything. But 7-inch effective length and 1/2-inch hex. That's what I want you all to do. Okay. There we go. Now, the first thing I want to show you all quickly is the differences between a hex shaft and thunder hex shaft. This is something that confuses a lot of students, but it makes sense when you kind of look at it. So hex shaft is just run-of-the-mill, it's a hexagon. So like, let's say I do a section view of this, section view, this, pull this back. So if I look at a cross-section area of a hex shaft, you can see it's just a standard hexagon. All 6 sides are the same length. the distance between two opposite faces is exactly half an inch. That's all you really need to know about hex shaft. Hex shaft will fit into a hex bearing. So here you can see we inserted a hex bearing. So hex shafts go perfectly into hex bearing. Thunder hex, on the other hand, is different. Thunder hex, if I do a section view of this, how did I do that again? Section view. Come on, give me that. Come on, let me do it earlier. How do I do a section view again? Section view, there we go. Section view, and I pull you back. You can notice that a section view of a piece of Thunder hex is actually, oh geez, what did I do? Oh no, I messed something up. Let me put these side by side. Hex is on the right, Thunder hex is on the left. I'm gonna section view them back. So you can notice that on a hex shaft, all a Thunder hex is a hex shaft that has rounded corners. So here on the hex shaft, on the standard hex shaft, we have a very sharp corner. It's what, a 120-degree angle or whatever. On a Thunder hex shaft, you round the corners. Basically, what they do is they take, or what you can do and what teams used to do in the old days before Thunder hex was made, you would take a piece of hex shaft and you put it on a lathe and you'd mill out the corners. And you might be wondering, why would you do that? The really cool thing about a Thunder hex shaft is it will fit into a standard hex bearing like this, but it will also fit into what's known as a Thunder hex bearing. So if I actually go into bearings, and you don't need to do this, I just need you to pay attention. If I go into bearings and I pull up a 1/2-inch Thunder hex bearing, here we go, 1/2-inch Thunder hex. Oh, that's a bushing. I don't want a bushing. Thunder hex flange bearing. There we go. So while a 1/2-inch hex bearing has a hex profile, a 1/2-inch Thunder hex bearing has a round profile. And so you might look at a bearing like this and be like, oh, that's just for a round shaft. No, it's actually for a hex shaft, and it has a very specific outer diameter that matches the outer diameter of a piece of Thunder hex. So if I section view this one more time, I pull you back, and I pull the bearing on top, you can actually notice that even though the hex shaft will not go into this Thunder hex bearing, the Thunder hex bearing will. And what it basically comes to is you have a press fit. So you are pressing the Thunder hex shaft into a Thunder hex bearing, and it will have 6 points of contact around the sides of the bearing. And so you might be asking, like, Alex, why do I care? Why does it matter? The key thing is that a Thunder hex will fit into hex. So a Thunder hex shaft will fit into either a Thunder hex bearing or a regular hex bearing. Regular hex shaft will only fit into a regular hex bearing. So I cannot fit this bearing onto this guy. The corners get into the way. There's some other advantages to this, though. One of the key advantages is that aligning a hex bearing aligning a hex shaft into a hex bearing can be very tedious. If you think about assembling like a full gearbox and you're trying to stick a specific shape into a hole of a specific size and a specific dimensions, that's actually kind of difficult. If you have ever tried sticking a hex shaft into a hex bearing, and you might have to go through other bearings, or you might have to keep other things in alignment, it's going to be very difficult. So if I say like put this guy here and then like rotate it ever so slightly, like those guys aren't going to fit together. This will no longer fit into this hex bearing until I get them properly aligned. And that whole aligning thing can just be a royal pain. I've done it before. Like just getting this alignment, and because the tolerances are so close, like The bearings and the shafts are made to such high levels of precision, fitting them into each other is just a pain. You don't have that problem though on a piece of Thunderhex, because since it's circular, it could be fitted in literally any orientation. So it does not matter which orientation you're sticking your shaft in, because you're fitting basically a round profiled shaft into a round bearing, into a circular bearing. So in a lot of cases, I prefer using Thunderhex. Rosie used a lot of Thunderhex, and any robot I design, I almost always use Thunderhex. There is one situation though where we prefer to use hex shaft. And the one situation is in a gearbox. The reason why we are going to use hex shaft, and the reason why, if you look at, actually no, 1678 uses rounded shaft. That is interesting. Oh, I think I understand what they did. We'll come back to that. There's another reason that just popped into my mind. But one of the key reasons you want to use a hex shaft with a hex bearing on a gearbox is because you can have extremely high torques in your gearbox. Imagine your robot like suddenly going from like top speed to slamming on its brakes or slamming in reverse. You could get a ton of torque in your gearbox. And with a piece of Thunderhex where you only have 6 points of contact in your bearing, and it's only a press fit, you can actually get slipping between the shaft and the bearing. And you don't want that. You don't want there to be extra movement between the shaft and the bearing. If you're using a piece of, if you're using a hex bearing, you don't have that problem. Because you can never, slip around these corners in a hex bearing. Now, you can use a piece of Thunderhex in a hex bearing. But the other issue that you run into, and the reason why you do not use Thunderhexes for gearboxes, is that Thunderhex is aluminum. And hex shaft that you buy from any place like AndyMark or VexPro is steel. And for the exact same reasons that I said why we should use steel gears instead of aluminum gears, you want to use a steel shaft instead of an aluminum shaft. So if you're ever going to have areas where you have an exceptionally high amount of load, such as a gearbox, you want to be using steel. So for that reason, we do not use Thunderhex. We will delete the Thunderhex for right now, and we will only use a hex bearing, and we will use hex shaft, steel hex shaft. Okay, undo that, delete. Last thing I'll say about Thunderhex for right now. Another key advantage of Thunderhex is that it has a hole down the middle that you can tap to a quarter 20 thread. Or anything that uses a quarter 20. So you could do 20 or 28 threads per inch. That's just really useful for retaining. You do not have that luxury on most steel hex shaft that you could buy. Okay, cool. Talked about hex shaft. Now let's just quickly look at the different options for how do you retain a shaft. So basically, how do you stop a shaft from falling off? There are many, many ways you could do this. The most popular ones that I see are snap rings and a bolt and washer method. So if you're a cool team, if you are a team that really has good manufacturing capabilities and you like doing things the right way, you will use a snap ring method. And we can actually see, if you look at 1678's CAD model, you can see that they use the snap ring method. If you don't know what a snap ring is, it's basically, another word is an E-clip or a C-clip. It's a little ring that goes around a circular profile. If I make this transparent here, oh, I can't. Basically, we can look at it on 1678's model. Basically, what they did is they put their shaft on the lathe, and they lathe out a little slot at the very end of the shaft. And in this area of smaller diameter, you fit an E-clip or a snap ring. And then you have a little area of a higher profile on the back to prevent the E-clip from coming off. And so you take your E-clip, you insert it in that in that lower profile that you can actually see right in here, and that will prevent anything from sliding off the shaft. So if you imagine you have a gear or some sprockets, those get stuck when they hit the snap ring on the end. So snap rings are great. They just take a little bit of work and precision to do them. One of the things you all noticed when you actually inserted this part is the effective length. The effective length is the amount of area between the shaft retention. So we have 7 inches in between both of these snap rings. So if you are going to do a snap ring method, you got to make sure that you are taking into account this extra amount of material that you lose. So in this case, you lose about looks like about 1/10 of an inch of material. So if you are making a 7-inch shaft and you want to use snap rings, you got to make sure your shaft is at least 7.2 inches long because you need to have snap rings on both ends. If we quickly change the configuration, if you right click on your shaft here on the left side and you hit change configuration, we can also look at other retention methods. The other really popular method is a bolt and washer method. I'm just going to change both ends to bolt and washer. This is what we predominantly use on Rosie because this Why is my voice so dead? Okay, we're back. Hopefully. Type a 1, 2, 3 in the chat if you can hear me. 1, 2, 3 from Tanuj and Aiden. Thank you. George Mason internet sucks, so I'm sorry. Hopefully that won't happen again. Where was I? I was talking about shaft retention, yeah. So, bolt washer. This method I like. It's a lot simpler than having to take your shaft to a lathe and put on an E-clip. But you don't really have that luxury if you have a piece of hex shaft that doesn't have a hole down the middle. So if we are running Thunder Hex, so like let's say we're doing an intake and we have Thunder Hex, I prefer this method. You'll see a lot of really high quality teams actually do snap rings for everything, and that's just because you get tighter. You don't have to worry so much about headroom. So here, as you see, when the bolt comes off, or the top of the bolt comes about 0.175 inches from the hex shaft, that's just wasted volume. And if you're trying to make a very neat package, you don't want to have this bolt head sticking out. That could cause problems, and it has in the past. Let's just look at one other configuration. This is something I never, ever, ever want to see you all do, and that is use shaft collars to retain your shaft. Yeah, it's but wow, it didn't even show us. It doesn't even put the shaft collars on here. Ugh. Anyways, don't use shaft collars. Shaft collars suck. I don't know why people use them still, but I never want to see a piece of shaft retained with a shaft collar. Shaft collars are great if you're prototyping. I do not want to see them on a robot. So what we are going to do is we're going to make sure that we are at a effective length of 7 inches, and we're going to change this later. We could just put it as something long enough for now, and we will fix it later on. We're going to make sure we're at 1/2 inch hex. We're going to make sure we're using snap rings because we want to be fancy and we want to use snap rings on our shaft. And then we're going to make sure include and merge everything. That just means it will include the snap rings and mate those. And yeah, so this is going to be the shaft we have. And now we are just going to mate the shaft onto into the bearing. So what I'm actually going to do is I'm going to do a mate, and I'm going to try grabbing. I have to do this another way. Okay, yeah. I'm going to grab the inside mate right there on that shaft ring, because the shaft ring should be flush to the edge of the shaft. I'm going to put my other mate right here in the middle of this bearing. And instead of fasten mate, I'm going to do a revolute mate, again, because shafts should rotate. And then I'm just going to revolve it once or twice to try and see if I could get it to line up. I'm going to rename this to main shaft. Cool. So it looks like it is a little bit off. That's going to annoy me ever so slightly, but whatever. Cool. So we have a shaft here that is retained on the left side. So now this shaft cannot be pulled out from the bearing because the bearing is retained on the other side. So now this shaft is basically stuck. You'll have to get in here with an E-clip in order to take it out. So now let's see what's next. I'm going to have to refresh this. Tanuj says, shouldn't the bearing be revolved and the shaft should be fastened? Tanuj, you are correct. The bearing should be revolved and the shaft should be fastened. You know what? Just because you called me out, I'm going to actually do that. Okay, change the main shaft to that, and the hex shaft, or that half-inch hex bearing should be edit. That should be a revolute. So yes, there you go. That is the correct way of doing it. Good notice, Tanuj. Now, technically, the bearing shouldn't rotate in here because it's only like the inside of the bearing that rotates and the outside of the bearing stays stationary. But Onshape does not do that, so we won't bother. Now, I'm just going to run a quick interference check because I noticed something. I did not do my mate correctly. As you all can see, there's a bunch of red here in the interference check, so I'm just going to go in here, try fixing this. I also noticed there's an error up here. This is why we do interference checks, because it is better to spot these type of issues now rather than later, because spotting them later means you're probably much further along your design and you're going to, fixing these issues would be annoying. How do I want to do this again? I don't want to grab the inside of the hex ring. I think that's what caused the issue last time. What I'm actually going to do is I'm going to do a fasten mate from you to you, and then I'm going to offset it. This isn't the best way of doing it, but it'll work. Offset by 1.102 inches, which I believe it was. This is going to be main shaft. I run an interference check. No interferences, that's great. Now I am interfering here ever so slightly. Just going to double check what this is. I can see that there's a slight issue here with my pinions. Really minor, but I'm kind of OCD about this stuff, so I'm going to fix it. What the heck? I caused another error. You'll just have to bear with me for a second. I'm just going to straight up delete you. Sometimes the best option is to just delete everything and start fresh. Revolute, 11-tooth pinion. Offset you by 1/4 of an inch. Okay, that should be good. I'm going to run one more interference check. Is my stream back online? Who knows? We back? Okay, well, it's not back on my monitor. Oh, there we go. You interrupted my sandwich eating. Aiden, the offset is 0.102 inches. That just purely comes from me measuring the distance from the back of the snap ring to the edge of the shaft. Anyways, before I was so rudely interrupted by whoever is screwing with George Mason Internet right now. What I was saying was that we were going to add this gear. Now, I don't remember what the gear number of gear teeth is. Does anybody remember? Because I don't. I think I can find it in here, though, if I go into here. 72 teeth. Yep, Tanuj beat me to it. 72 teeth. So, what I want you all to do, go into MKCAD, find the 72 tooth, 20 DP steel, hex, half-inch hex bore gear. So MKCAD, we're going to go to gears. I'm not going to do configurable gears because I don't really see the point in that. Actually, you know what? Screw it. I'm going to do a configurable gear. Because I can. And I'm going to do the 72 tooth gear. Oh no, wait. No, we're not going to do that. Because specifically, I want the pocketed gear. Now, pocketed gears are great. Sadly, they don't make steel ones above 60, which is very annoying, so we're going to have to go with aluminum here. That's not too bad because it's such a big gear. A pocketed gear is just something that is... you can see what the visual differences are. Standard gear down here, pocketed gear up here. The only important parts of a gear are the teeth and the bore. So everything else here is kind of like useless. So you could buy these gears from Vex Pro or West Coast products that have a lot of that wasted material milled out, and that just saves you a little bit of weight. There's no reason not to do it. And that's specifically what 1678 does. So I'm going to take that, going to mate, rotate, fix, rename 72 tooth gear, and boom. We are Gucci. Now I do want to make sure that we do not have any chances of interference. Now, one thing with these gears is they do have a little bit of a lip to them. They have about in this case, that's like a 1/16 inch lip. Where it basically acts like a mini spacer. Which gear again, sorry? The 72 tooth pocketed aluminum gear. So I'm looking at this, and this is great. Personally, this amount of distance, this is like a 20th of an inch or something. That just kind of makes me uncomfortable. I don't want that this gear to be this close. If anything happens and this gear starts brushing up against that plate, you're not in for a fun time. So it does seem like Team 1678 gets away with it. Yeah, no, we'll accept it. Personally, what I would do is I would take like a 1/4 inch spacer and stick a 1/4 inch spacer back there and just pull the gear out a little bit. But if Team 1678 says it's okay, then I say it's okay. Now, if we look at this, if we look at Team 1678's gearboxes, I'm going to just make this transparent quickly. They seem to make... Try and see how they might offset the pinion from there. They really don't, but they also won't interfere that hole, so I guess it doesn't matter too much. Basically, what I want us to do now is modify the mate features with the 11-tooth pinions and change them from like -1/4 of an inch to -0.1 inches. And because you all named your mate features, it is super easy to find out where these mate features are. And pick some. Cool. Now all of that's working. So I'll leave you a second just to get that in. Cool. So let's just keep rolling on. The next thing we're going to do is we're going to insert these sprockets, chain sprockets. We're going to do 18-toothed half-inch hex bore 25 chain sprocket. And I'll explain a little bit about chain here in a second. So we're going to go into MKCAD. We are going to go down to sprockets. Do they have sprockets or is it like pulleys? Sprockets and chain. Here we are. Sprockets and chain. We are gonna look up. Now I'm looking at the configurable one. Doesn't really matter which one you do. The specific thing is we want number 25 hex sprockets. And we want single ones. You can buy them double, which is a lot of what a lot of teams do. But Team 1678 does 2 single ones, so we're going to do number 25-inch single sprocket. We're going to do an 18-tooth. We're going to make sure we're doing a half-inch hex bore. God, I just cannot speak right now. And then we're going to copy that, and I'm going to duplicate it. So I will drop the part number. I'm going to just, drop that number 25 half-inch hex sprocket 18-tooth. Shrethi, you say, I keep missing which parts to select for the mate. Is there any specific part you're still on? I will come over to your document. Actually, apparently I don't have your document open. Yeah, sorry. I tend to go through those a little bit fast. CAD is a fast thing. So, for this hex shaft, what I was doing is I mated this end, to the very far end, to the outermost part of this bearing, and then I offset it by the distance between this end and the spacer, or the snap ring, which in our case is 0.02. Or, sorry, 0.102. 0.102, correct, yeah. Just whatever that distance is. Because it's kind of hard to grab the center of this snap ring because snap rings aren't perfectly circular, which is part of the reason they are snap rings. Anyways, so hopefully you all pulled up these sprockets. Shaft is not mating correctly. See if you can get it now. Yeah, so now you have it. Let me know if you're still having issues with it. So hopefully you all got these 18-tooth sprockets. Now we are just going to do a very simple fasten mate to the gear. Technically they should be fastened to the shaft, but it's not trivial to do. So we are just going to do a fasten mate to the gear. We're going to rename that 18-tooth sprocket. Ah, man. Whoever's working at George Mason IT needs to be fired. We need to bring in some competent people who know how to run our internet system. I think I'm back though. So while I prepare the next bite of my sandwich, I'm going to fasten mate on this guy to this guy. Okay, rename that 18 tooth sprocket. Oh, my sandwich almost fell. So hopefully you all are at this point. Please feel free to speak up if you are stuck somewhere prior to this. But we now have both these shafts mated. My OCD is mad that I did not capitalize the T's in tooth. They are in the MKCAD library, so I'm just going to fix that quickly while I wait for anyone who might have questions to type them. No questions? Okay, then we shall continue. Let's see, what is the next thing? So the next thing really looks like we just have this plate, so we need to design another plate. Specifically, this plate is going to interface with the drive rails on the frame of the drivetrain, and it is going to serve as an offset for the plate holding the motors. So as you can see, we have several spacers here. And they have some PEM nuts, and we'll learn about PEM nuts here in a bit. Yeah, let's go ahead and start making another plate. So we're gonna have to go into the parts studio for this. So there's several ways that we can do this. Onshape's annoying me right now. Everything's annoying me. Internet's going out. My Onshape is messing with my key bindings. Aiden, can you review how to mate the 72 tooth gear? Yes, I can. So the 72 tooth gear mate, if I delete that quickly, basically all you're gonna do is you're gonna do a fasten mate between the lip of the 72 tooth gear, and you are going to mate that straight to the middle of the bearing, because the bearing is a revolute mate. So that's what we're gonna do for that. All of your other parts are just mated onto that as well. One cool thing we can do with all these revolute mates is we can do a gear assembly, and I'm going to show you all this quickly. If you do a gear relationship between the half-inch hex bearing, where you have the 72 tooth gear and one of your pinions, and your ratio is 11 to 72, you can actually make gears that work with each other. I don't know if this is actually working. Might have done the ratio backwards. Oh yeah, they're also moving in the wrong direction. First direction, 72 over 11. Yeah, I think that's better. Yeah, so you can actually get them to kind of rotate together. You can do some cool stuff with that. I don't particularly care though. What's the name of the spur gear? The spur gear is the 72 tooth pocketed one. So it's going to be way down in the MKCAD gears. You might want to go to their MKCAD configurable gears, honestly. But you're going to do this one, 72 tooth 20 DP aluminum half-inch hex bore pocketed gear. West Coast product number 0123. So hopefully you all can find that. I'm going to go ahead and start on the next part. What are we calling it? The next gearbox plate. So there are multiple ways you could do this. I'm just going to start fresh and use the current plate as a reference. Oh no, what happened? I seem to have an error in my extrusion here. Let me just fix that quickly. It's not good. Give me a second while I fix this. Yeah, if any of you want to get started on making this plate, go ahead. The key thing is that you need to make sure that the mounting holes for these outer two holes down here, the outermost ones on the lower two sims, and the mounting holes for the middle sim are the same dimensionally for this other plate because those all connect together. I'm gonna try and figure out what's going on here with my sketches. It's like that's good. Oh, it's not. These aren't good. I'm gonna make you and you intersect, and I'm gonna figure out why, among all of these error reasons, why this is being an issue. Honestly, I kind of made this drawing kind of crappy. I should go in and fix it. You should be. You and you should be coincident. Giving me an error for some reason. Hit you. Whenever you have blue, that means it's bad, as you all know. So if you ever have blue things, you should try your best to break it and see what the issue is being caused by. What the heck is that? Yeah, I might just honestly straight up delete you. Try and figure out what is the cause of this. Oh, that might be an issue. Should be coincident with you, and now you're causing issues. You are correct. You are correct. Ah, I see what the issue is. You need to be deleted. You need to be offset by 1/4 of an inch. I'm just gonna remake these guys quickly because they keep causing me errors, so. Oh. Just give me a second here, guys, sorry. This type of stuff will happen inevitably when you CAD. Okay, main sketch. Fix my extrusion. Extrude you. Okay, good. So that's all good for right now. Okay, so now we are going to move on to the next plate. So I'm going to hide this current plate. I'm going to start a new sketch. And I'm going to go over here and I'm going to isolate 1678's robot, this main plate, and I'm just going to see kind of what we're looking at here. So we have a center hole. That's going to have a diameter of 1.115 inches. I do not know why, but we're going to just do it for that reason. I have that be exactly the same. Now let's see. Now there's two mounting holes here to the left and right. And those have a diameter of 1/4 of an inch. And they are 0.9375 inches away from the right. That's oddly specific because that is, what, 15/16? Which is interesting why that is. So I'm going to go back into my drawing and I'm going to do 2 1/4-inch holes. And actually, one thing I'm going to do here that I didn't do last time is I'm actually going to CAD this part in half. I'm going to make the left half and then I'm going to mirror everything over because that is how you should, that's how I should have done the first part. So I'm going to make my amends here. And do that because that will save us half the work. So we have 2 holes. One is 1.115, the other is 1/4 inch, and they're offset by 0.9375 inches. Quickly, I'm going to answer Aiden's question. Aiden says, my 11-tooth pinions aren't lining up with the keyhole. Is there an easy fix? So probably what is happening is if I delete one of my 11-tooth pinions, what might be happening is you are not actually grabbing the true center. So if I mate here, you might be able to notice that the center, if I click on the face of this 11-tooth pinion, and the center of this hole are actually slightly offset. You can see how that mate icon is moving ever so slightly between whether I click on the face or whether I click on the edge of the hole. That will cause you issues if you do your interference checks. So make sure you're grabbing the center of the hole, not the face, the center of the actual hole itself, and then grabbing the very center of this face as well. That might fix your issue. But anyways, I'm going to get back to the sketch. So let's see. One thing I'm going to do here quickly is I'm going to, along this vertical line, I'm going to add just one large construction line. That is going to be our mirror line. Stop doing this on shape. Gosh. Okay, cool. So now what else? Let's go ahead and mark out the location of these other holes because those seem important. So I'm going to mark the distance between, well, let's see. This hole is 1.91 inches, which is 3/16 of an inch, I believe, approximately. That's not what I wanted. I didn't want Bible stuff, but it's approximately 3/16 of an inch. They're probably using a 3/16 inch bolt plus a little bit of tolerance. And that is exactly that much away. Oof. That seems a little bit arbitrary, so let me see what the distance between these two is. That also seems arbitrary. Who knows? We have a little bit of tolerance there. So this is going to be about 3.06 inches away. So I'm going to put a third hole over here to the right. And that is going to be 0.191. This is going to be 3.06 inches. And then we're going to do one more, which is going to be the hole up here. That is again 0.191. And you are, we measure the distance, you are 0.72 inches to the left and 0.153 inches up. Grand total of 1.676 inches at a diagonal. So I could just kind of arbitrarily place the hole at that point. I could use 2 dimensions to mate the hole to the proper location. What's this again? 1.513. 0.513. And we can always adjust these ever so slightly later if need be. So I'm going to let you all CAD those quickly into parts. If you ever need these dimensions again, you can either obviously go measure them directly off of 1678's robot, or you could just come to my part studio and copy them off of me. Not saying I'm doing this assembly perfectly, I'm just doing them. So if you're already at this point, what you could go ahead and start doing is the exact same thing we did with the other gearbox plate. What you're going to do is you're going to offset these holes, and then you're going to connect them all together with a bunch of lines. If you all remember, this is all you need for a plate. If you are going to CNC a plate for a gearbox or whatever, all you need is the holes, the location of the holes and the diameter of those holes. And then in order to finish the plate, you're just going to offset them, you're going to make them bigger, and then you're going to connect them all together, which is exactly what 1678 does here. So we are going to do exactly that. We are going to use the offset tool, which is here. No, that's concentric. Where's the offset? Here it is. We are going to offset all of these holes by 1/4 of an inch. Up. I can only offset a single chain at once. I forgot about that. Offset U. Offset U. You don't need to be 1/4 of an inch. We'll make you 1/8 of an inch just because you're a smaller hole. Offset U. I'll make you 1/8 of an inch as well. Offset U by 1/8 of an inch. Okay, cool. So I'm just going to use the trimming tool, get rid of that. I'm also going to get rid of U as well. I just kind of get rid of some of the why does my shape keep zooming out? Using the trim tool, I could just get rid of some of the extra stuff. Now, what I'm going to do is I'm going to actually mirror. Actually, no, I won't mirror quite yet. I'm going to use some lines here, and I'm just going to connect these parts together and make sure everything is a tangent mate. U, tangent U. Same thing for down here. Line across here. You are going to be a tangent mate. You are going to be a tangent mate. Cool. I'm going to do a line from here to here. These are going to be tangent mates. Chinju says that dimensions for me are different. Like the 0.72 and the 1.513 are edge to edge and not center to center. Really? Did I read these wrong? There's no way. That one's right. This guy, this guy. Wow, you are right. Somehow I measured the minimum distance, even though it was up here. I need to measure the parallel axis distance. Good catch, Tanuj. So we actually need to change that. We need to change the offset to the left to be 1 inch, and the offset up to be negative 2.103. So I'm going to change that right here. You should be 2.013. Was it 103? Let me check. 103. 2.103. And the offset here is going to be 1 inch. Good catch. I would not have noticed that until we actually tried assembling them in the port studio. Hope I did not make that mistake anywhere else. So quickly, I'm just going to add these other mates. Make these tangent. You to you. You and you are going to be tangent. Now I'm going to use the trimming tool, and I'm going to just trim away some of this excess. Trim away you. I'm going to trim away you. You can be trimmed. I won't bother with you. Now one other thing is 1678 has this circular protection device type thingy. I guess probably mostly to prevent any fingers from getting into the gears. But I'm going to add this as well. It has a radius of 1.87 inches. So from here, from the center of this guy, do 1.87 inches times 2 because that's the radius and we need diameter. I'm going to trim the top because we don't need... I'll leave it for now. That's not what I wanted. I'll leave the right side for right now. I'm going to offset you inwards by 1/4 of an inch. I'm actually going to lie down a construction line here to the left. Just so I could trim away these two guys. Actually, honestly, I could just do... Who am I kidding? I don't need that construction line. I'll just do the left side and I'll mirror it later. Just make sure you're constrained to you. Both of you are constrained down there. Okay, cool. 1678 does add a, like, arm right here. I don't really know why. That seems unnecessary to me. Also, this hole here is massive. I feel like that is unnecessary, and I'm not going to include it. Or, like, the amount of space they have around this is unnecessary. It might become necessary later for a reason that might become present in the future. I have no idea. But for right now, this is how I am doing this. If you all want to more closely follow the assembly, be my guest. But I am going to do it like this for right now. Now I'm just going to add one straight up and down line. That is going to be 1/8 of an inch between you and you, and I'm going to trim off you. And there I have basically the entire left side of this plate done. Now I'm just going to mirror everything. I'm going to take the mirror tool, and I'm just going to start clicking on all of the different features that we made thus far. You, and you. Now everything is shaded, which means it's fully good. The last thing I'm gonna do is I'm gonna just probably should have done you with a mirror, but whatever. Just gonna add in 2 extra lines above here. And I'll just offset you by however much. 1/4 of an inch. And then I'm going to just trim off you and you. This is one thing I didn't do on the last assembly. Was I did not do any trimming, which I definitely should have done because it would have saved me a lot of time and effort in extruding. Oh, the other thing is I need a bridge between here and here. And Jeannie says, hey guys, I'm going to have head out for now, but I'll catch up sometime later. Awesome, see you later, and Jeannie. Good work catching up this week. Yeah. Cool, so we are going to very quickly... where do I want to bridge those to? Particularly matter. Let's do a line from you to you, maybe. You tangent up. That's not what I wanted to do. Maybe I can make you and you normal. Nice. Just gonna do a second one. I'm gonna offset you and you by 1/4 of an inch, and I'm gonna make both of these guys parallel using a parallel constraint. That Oh, I tried saying it. I had 25 degrees, not 25 inches. Okay, cool. Then I'm just going to mirror that. My voice is really dying. Holy crap. Then I'm going to trim these guys. What? So this is one thing I hate sometimes is when you trim a part and then suddenly everything becomes unconstrained. In which case you might just have to re-add a constraint, which might be okay. If you ever trim something and it removes like the entire world's worth of constraints, just don't trim it. So apparently getting rid of that little edge of a circle right there makes Onshape hate me. So I am not going to get rid of that. Okay, cool. So I kind of brushed through that, mostly because I expect you all know how to make parts. I mean, it's pretty simple. All you're doing is finding the exact dimensions that you need for the holes, and then from there you're just making sure that you have enough material everywhere to make sure it's solid when you actually CNC it out. So I'm gonna go ahead and finish up that sketch, and I'm gonna rename you. I'll just rename you main sketch. I always like renaming my sketches because it helps me keep track of them. Now I'm going to extrude this entire thing by a 1/4 of an inch because we are using 1/4 inch plate. I'm not going to rename the extrusion. I am going to rename the part though. This is drivetrain part 002. And this is going to be, I don't know, secondary gearbox plate. That's just whatever I'm going to rename it. Then I'm going to add both of these to a folder and name them part 002 or P002. And there we have it. That is our plate. It looks kind of different than 1678's, but you know, we are special and we are unique. There are some things I don't like. I don't like this. That just kind of makes me nervous, how it pinches in so much there. That seems like a point where it'd break. So I'm actually just going to go into my sketch and fix that. What I could do is I can basically continue this line. And make you instant for you, and then I can make you and you parallel. Why my Onshape keeps zooming out? To you, and then you and you parallel. You and you parallel. Trim that outer part. Oh my god, stop zooming me out, Onshape. Why are you doing this? Why do you hate me? Maybe I need a new mouse. Okay. That to me just looks a whole lot better. So the only other things we are going to do here, well, there's a few things we need to do. I'm going to stop right there. Feel free to ask any questions with this plate before we move on. Is anyone like having any issues or is confused? Or do you think you all got this? I see you're making a new feature, Shrethy, so you're still in that part. And Genie, that you leave. So Tanuj, one thing that I see you have is you created a new part studio where you're creating, I assume, this new plate. Um, I strongly recommend creating everything in the same part studio. So as you notice down here at the bottom, you already have drivetrain part studio. So I would make that a new part in the same drivetrain studio. And that's just gonna make it less confusing if someone goes into your CAD model and tries to change something. They don't have to look through like a dozen part studios to find the part they're looking for. They just have one part studio with all the parts. Aiden, I see you have your sketch here. Nice. So the only thing I might do is I'm just gonna make this a little bit more efficient, I think. Let me change my sketch. I'm gonna just kind of make these thinner. You guys don't have to do this if you don't want to. I would be happier if these guys were. Ooh. Hmm. If I make you and you coincident. Trim a little bit of space. I'm just kind of messing around with stuff, seeing if I could make these more efficient. You all do not have to do what I am doing right now. This is just me being weird. What if I make you horizontal? Shrethy says, could you zoom out so I can see all the dimensions? Yes. These are all the dimensions for the left side. And I mirrored everything over to the right. You all might have slightly different dimensions from me. That's perfectly fine. Everyone's gearbox plates can be unique as long as the holes match up. That's really all that matters. Feel free to take a screenshot as well if you need them. Okay, so I'm going to continue quickly, just so we could kind of get to a few other key points today before we wrap up. So again, whenever we create a part, there's a key thing that we need to do, and that's always assigning our material. I don't know if we did this last time actually, but this is one thing that's very important to do. Whenever you create a part in Onshape, always, always, always assign your material. So if you right click on your parts in your part studio and you hit assign material, you can pull up the Onshape part library. So what these parts are they're both 6061 aluminum. So I want you to change both of these parts that you've created to 6061 aluminum. You can just type in 6061, it'll appear. The second thing I would recommend doing is changing the color scheme of both of them. Onshape likes to auto set the appearance I prefer going in and changing all of the color schemes to what they'll more naturally look like. So in the case of aluminum, you want something that's gray. And this is just helpful so when you actually assemble your parts together, it looks realistic. Or when you assemble your parts together, it looks realistic. So I am going to go ahead and test this secondary gearbox part, see if it actually aligns how we want it to align. It doesn't. Ooh, we have issues. We have problems here. What might those problems be? Who knows? Let us do a temporary mate, and I'm just going to title this mate temp. Just mate the center view to you. And I'm going to align these parts together to see what the issues are. So my top two holes look great. But it seems like these edge holes are not. So I'm going to go check these again on 1678. Distance from you, 3.06. Distance from you, 3.06. So why are we getting offset error? How small are the two mini holes on that second plate? All of the holes should be these two holes right here, right by the big hole, is a 1/4 of an inch, and everything else is 0.191 inches. Negative 3.06. Huh. Let me take a look at our main drivetrain gearbox. The distance between you and you should be the same. I get 3.103. I'm wondering if we're running into interferences somewhere else. What is that on 1678's robot? I can check something here. Isolate. Isolate. Distance between you. Oh, I know what it is. So the issue, one of the things I didn't do, that 1678. Oh, hey Timmy. I'm just teaching students CAD. I have identified the issue, and the issue is that if you look here on 1678's CAD, they actually tilt their motors ever so slightly. So there's like a 20-degree angle here on their left and right motor. And that is because I assume they wanted better alignment for their wiring. I didn't bother to CAD that in. So our measurements will not be identical to 1678's. So I need to take this exactly from our part studio, which is distance between the center of this hole and the center of these outer holes is 3.103. So I need to go back into our sketch and fix that dimension 3.103. And that should fix that. As you can see, it does perfectly. Cool. So let me check on all of you. Shrethi, I see you got half of that CADed. I will pull open Sketch again in case you want to see it. Actually, you should actually be able to go into my Sketch and see all those dimensions directly as well. Aiden, I see that you have your part as well. I'm going to just check that dimension here. So it seems like your distance is a little bit larger, and you might have that same issue too when you actually insert it into your main assembly. Just go ahead and check that. So what we want to do now is we actually want to get into mating the two plates together. But I will not do that until Shrethi has finished their part, and so has Tanuj. What I think I'll do is I'll actually start wrapping up here today, just because it is almost 8 p.m. What I'm going to do is I'm going to show you all quickly how I make these spacers, and then by next week, I want you all to have these gearboxes fully done. So you're going to have this plate finished, and you're going to have the 4 spacers that go in between them. Next week, we will add in these the actual drive rails along with this, and I'll also show you all how to add in all the bolts and nuts and whatever. So yeah, let me just grab the distance between these two plates that 1678 uses. The parallel distance is 1.408. And so making spacers in CAD is obviously very simple. It's just 2 circles on top of each other. So our one set of circles has an inner diameter of 1.191. So we might just want to give it an extra little bit of clearance. So we might say, like, let's do 1/4 of an inch. The outer diameter is, let's say, 0.75 inches. Let's make it 1/2 an inch. So I might have you extrude you out to 1.408. And that might be my spacer. I'm going to insert that just to show you all. I could just simply mate you onto you, and there you have a spacer. And so this might be an example of spacers I would include on my gearbox. Very similar to how 1678 does their spacers. We will have spacers just like that act as standoffs, and then you run a bolt through the entire thing that will connect that motor to this front plate, and that will sandwich everything together. Typically, we 3D print these spacers, so you could just make them out PLA. You can make them to whatever dimensions you want, and we'll 3D print those. Or you can actually go out and buy custom nylon ones, or buy nylon ones, and then you machine them down on a lathe. That's too much work. 3D prints are great. But yeah, that's what I want you all to get to over the next week. Just make those spacers. You don't have to make them exactly how 1678 does. Like, for some reason, this one down here is just absolutely massive for no apparent reason. Just make sure that the inner diameter of them matches the diameter of these holes, or is larger. That's it for tonight. Any questions before I leave and let you all go for the night or finish your CAD? So if the second plate is too long, do we just shorten it? Yes, exactly. the distance between the center hole and the outermost hole should be the exact same as the distance between the two respective holes on your main plate. So simply go to your main plate and then measure the distance between your center hole and your outer holes. And you will get it. Your secondary plate is just your main plate minus all the extraneous holes. So it's, this hole and then these outer foremost. So as long as all of these dimensions are exactly the same on your secondary plate as the main plate, or the dimensions of these 4 holes should be exactly the same between the main plate and your secondary plate, then you're good. Quickly add these to a folder. I'm going to rename this drivetrain 003 Gearbox standoff 1. I'm going to assign material PLA. Or to assign appearance. I don't know what I want the appearance to be. I like changing PLA parts to bright orange sometimes. Then I am going to add these just so you all can see kind of what I'm expecting by next meeting. Start adding these to my assembly. Very plate. Spacer. This has a radius of 0.2205. I'm going to fix that on here quickly. Just so those match up perfectly, because that makes me happy. I'll add these here. Spacer. Spacer. Cool. So this is where I want you all to be at by next meeting. Exactly what I have here in this assembly. I'm going to run an interference check. These are acceptable interferences just because that's bound to happen. So I'm not going to worry about that just because that is easily adjustable. Now, it's good. Cool. So it's almost 8 a.m. or 8 p.m. Sorry. I'm going to shut off my live stream, and then we will talk briefly in the Discord before we wrap up the meeting tonight. So I will talk to you all in the Discord in a few seconds.